All right, welcome back, everyone. Today we will be covering the third part of optimizing IO tutorial. My name is Ritu Arora, and I'll be the instructor for today's topic as well. And my contact information is available on the slide. Please feel free to connect with me or reach out to me with any questions that I may be able to help with at any point. So like I was mentioning today, we would be covering IO in the context of checkpointing and AI. Previously, we have covered how to optimize IO or why to optimize IO. We have worked with some general IO strategies for working on HPC platforms. We discussed about the Lustre parallel file system. We discussed the parallel IO patterns and MPI IO. And today the focus is going to be IO in the context of checkpointing and AI. One more time, I wanted to remind you all about the pre-event survey, just in case you haven't had a chance to take that yet. Here's the link on the slide and in the email invite I sent this morning. I've also included the link to this survey. I will pause for a bit to give you a chance to go to this link on the slide and respond to the survey questions in case you have not taken the survey before. The pre-event and post-event surveys help us in measuring the impact of our training, education, and outreach activities. And hence, I've been requesting to take the survey. So pardon my badgering on this one, but I request you all to take the survey in case you haven't yet had an opportunity to do so. I'll be quiet for a few moments so that you can catch up with the survey now. All right. Now here's the link to the Google Doc for the Q&A session. To keep track of the questions and answers and to be able to access them even after the meeting, I would request you all to please note your questions as they arise in the Google Doc, whose link is here on the slide. I'll periodically pause to take questions after covering every few slides. And just a reminder again, this meeting is being recorded. All right, let's consider some situations that we have encountered in the past while working with the customers on shared computing platforms. It is not unusual to have customers who have jobs that take longer time than the allowed default time limits in the queues on the HPC platforms. And then they write to us with requests to extend the runtime of their jobs. So here are some samples of the queries we've got. These are actual queries, just the sender name has been changed at the bottom and the queue name and the system name has been changed. But this is exactly the type of messages we get, or I used to get in my previous jobs. And in addition to such requests, wherein people would request for increasing the job time because their applications would take a lot longer time to run than what we allowed on the system. There, you might have noticed certain announcements like what you see on the screen now. So oftentimes, Lustre file system goes down, and it's and once the Lustre system goes down, it impacts the activity of everyone working on the system. The compute jobs go down, and typically you would see messages like the object storage server of the Lustre file system is having problem, or the storage target is down, or the metadata server is unresponsive. So such situations are not unusual as well. So you've seen both sides, as in the request from customers and the type of messages sent from the system administrators about the system going down. Now, given these situations or this context, the question that arises is, do we extend or not extend the job runtime beyond the default values for everyone who asks to do so. So there are situations wherein we have been able to talk to the customers we've been supporting, look at their applications and suggest them workarounds such that they do not need any extension in the job runtime at all. So but however, there have been certain times when the research and exploratory work has been such that there was no workaround but to grant the extension in the runtime. And when there have been occasions when we have extended the runtime from, let's say, our default policy of 72 hours maximum for a particular queue, we have extended for, let's say, a month even for certain customers. Even then, there are issues. The issues range from the system going down for emergency maintenance, for example, or let's say when we have to apply a security patch, urgent patch, and then we have to take the system down. So when we take the system down, then this long running job, let's say, which has been running for 20 to 25 days, now will also go down or will be paused. So the whole time spent in running the job or computing in this duration is going to go waste. And then there are certain situations wherein people are running machine learning or AI jobs, wherein they have to go back to the previous epochs or the intermediate results that they're saving and inspect the results and see if they are stuck in local optima or they want to improve the results any further. So in such situations, basically, it's very important that we have a mechanism that helps people to pause the jobs and resume the jobs at a later time without starting from scratch. And that mechanism or a mechanism like this is called checkpointing. So we will be talking about IO and checkpointing today. So let me just give you a brief overview of what checkpointing is. So checkpointing is the process of periodically saving or writing the execution state of an application such that in the event of an interruption in the execution of an application, the saved state can be used to continue the execution at a later time. Typically, the execution state is written to a file, and then once the application needs to restart, this file that is saved or the checkpoint file is reloaded in the memory, and the application resumes from the point where it stopped before the system went down or when the application was paused, instead of starting from scratch. Now, when the second phase, when we are restarting the application from the saved state or a checkpoint, that's called a restart phase. Checkpointing not only saves time by offering the capability to resume the execution of an application in case of a hardware failure in the underlying computing platform, or if the computing platform becomes unavailable due to emergency maintenance, but it also helps in overcoming the time limits associated with the different job queues or partitions. Additionally, like I was mentioning earlier, for AI models that can take very long time to train, checkpointing and restart can help in inspecting the intermediate results during the inferencing and the model training process. Now let's look at the various forms of checkpointing. One form or one type of checkpointing that is popular is system level checkpointing. It involves taking code dumps of the computational state of the machine or system on which the application is running. For example, Berkeley Lab checkpointing and restart tool is a very well-known package for system level checkpointing. This approach has its own pros and cons. While it's convenient to use and there are no code changes required, the user only specifies the checkpointing frequency, so it's very convenient to use a tool like BLCR. However, there are very large memory footprints for checkpoints that can be created for the entire execution state of the application, and the operating system processes are also saved. And one needs system level privileges for installing this code on the system. The other form of checkpointing is library level or user level. This involves the use of libraries for taking checkpoints while being agnostic to kernel level information such as process IDs. So one popular tool that does library level or user level checkpointing is DMTCP. The advantages of using this tool are that it's useful for checkpointing applications without requiring any changes to the source code or the operating system kernel. The disadvantage is that the users may need to load the checkpointing library before starting their application, and then would need to dynamically link the loaded library to their application. And the checkpoints can have very large memory footprints as well with this approach. Not to mention that till last time we checked or worked with DMTCP, it did not take care of checkpointing all the applications as well as we had expected. It worked well with R, it worked well, I think, with multi-threaded OpenMP code and serial application, but I do not remember it working well with parallel applications or non-threaded parallel applications, to be precise. Other form of checkpointing that I should mention here is application level checkpointing, and it involves implementing the checkpointing and restart mechanism within the application itself. Now, the advantage of this approach is that it's very efficient in terms of the memory footprint, and because you're saving only that is required or what is required to recreate the execution state of the application at a later state, the speed at which the checkpoints are written are also small, is also quick. So the time involved in writing checkpoints is small, the size of checkpoints is small. However, the onus is on the customer or the developer to identify what to checkpoint and where. However, if you're writing your application from scratch and you're familiar with the logic of the application, then you should be able to identify what is it in my application that I should absolutely save to recreate the entire execution state of the application during the restart phase. Some of the popular applications that support the feature of checkpointing and restart are Flash Astrophysics Code and Abacus. And today, this would be our focus of conversation, as in application level checkpointing with different programming models and packages. And I should mention here that depending upon the frequency of checkpointing, the type of checkpointing mechanism, the amount of data to be written in the checkpoint file in general can vary, and hence checkpointing can become an IO intensive activity. And that's why it's relevant to this topic of optimizing IO. Therefore, it's important to consider optimization of IO when we are writing checkpoints and during the restart phase as well, so that we are not incurring large overheads during IO and we do not have large memory footprints. So like I said, today we will be covering examples of implementing application level checkpointing in serial and parallel applications written using different programming languages and frameworks. At the very onset of this whole process of identifying how to do application level checkpointing or how to implement it in the code, it's important to understand this concept of critical variables. So critical variables are those variables whose state we cannot compute or find by looking at the state of other variables in the application. So let's see or take a look at this code we have on the right side of the slide. So it's a very simple code. It's int main, int x is equal to 4, int y is equal to square root of x, int z comma I, int j is equal to x multiplied by y. For I equal to 0, I less than 100, I plus plus. Then we have z equal to z plus j multiplied by my function, and it takes random number multiplied by I. And then we return 0. This is a very tiny program. I would give you a moment to inspect what's going on in here and see if you can identify if there is anything in the code that can be recomputed using some states of other variables or values of other variables, and something which is very difficult to recompute, or maybe something which is very difficult to find the value of in the phase of restart. So here, if you see x is equal to 4, so when we compute y, the value of y is dependent upon square root of x. So x we already know is 4. So neither X nor Y are critical variables because Y is derived from X and X is hard coded to 4. So these cannot or should not be our critical variables. Then we see J. J's value depends upon the value of X and Y, which are again not critical. Since X and Y are not critical, J is not critical as well. Now let's look at the for loop variable I. I varies from 0 to 100. So in the event we have to recreate the application state, we do need to know what was the value of I before our code was interrupted in its execution. And in addition to this, we also need to know the value returned by the my function, which is not saved here. So FCT is short for function, like JCT is short for junction, FCT is short for function here. So there's this function called myFCT. I haven't shown this on the slide, but it's using some random number to calculate, let's say, the value of the variable z. So it's returning certain value which is multiplied by j, and that's how we compute z. So I would say in this code that we are looking at, we should be saving the value of I and z to recreate the state of the application at the later point. And hence our I and z become our critical variables. Now let's look at a sample code snippet. Let's say you've identified your critical application variables. So what would you need to do in your application to create this mechanism for application level checkpointing, or basically your application can save the state and read from it and restart at the later point? So the whole code for this application is in the GitHub repo, whose link I've shared here. And then here you would notice that basically in the repo, basically if you go, you will see that there's a non-checkpointed version of the code and there is checkpointed version of the code. In the non-checkpointed version, you would notice that we do not have the mechanism like we have here. Like if I is equal to rows start, then do something else, do something else. So basically we have to put guardrails, or we have to put safeguards at different places to tell our program that if you're restarting, then do something else. When it's a normal course of execution, do something else. So you have to depend on your if-else statements to build this logic in your code. And then you would need to have logic in your code wherein you can say that, for example, here we're saying every fifth iteration, write something to the file. So we're saying imod 5, which is every fifth iteration, save certain values which we have identified as critical variables. So we're saying save the value of I and v, print those to a file. So this is the kind of mechanism that you would need to build. Your checkpointing frequency can vary. You can make this as a variable and accept its value from the command line, such that a person or the customer who's running your code has the flexibility to change the frequency of checkpointing. They can say checkpoint every 100th iteration or checkpoint after every 10 iterations. So rather than hard coding this value, you can make this as a variable in your code. And of course, you have to remember that when you are restarting, you should have appropriate type of arguments that you are passing to the code. And then the code should be reading those arguments, parsing those, and then taking action accordingly. So you can have a flag, let's say R for restart. So if somebody is running your application with flag R, you know that, okay, then that means somebody is wanting to read the values from a restart file. And if you find this flag R passed from the command line, you can set up your logic such that you can say, if restart, then read the value of certain variables like row start or v from the restart files or the checkpoint files, rather than initializing them by default. So these are the type of changes that you would need to making your code. So in summary, I would say the maximum effort would go in identifying the critical variables whose state needs to be saved for your application in order to implement the application level checkpointing in your code. Now let's look at a Python example. So when you're working with Python, it's very convenient to implement something like application level checkpointing using certain libraries and packages that Python provides. Python supports object serialization and deserialization through its pickle module, and the detailed information on pickle is available in the Python documentation. I would recommend that you take a look at that, as in read about what pickle is and how it is used. I'm showing here a small example of how you can use this package. So this is a 29 lines long program, not very long, but just enough to demonstrate how to use pickle to save the state of certain variables, and how to use the saved state and restart the program. So at line number 3, you would notice that I'm having a call to the pickle package. I'm saying import pickle. And then in line number 14, if you notice, I'm saying use pickle.dump to convert the data, which is the value of A here, into byte stream. And this byte stream is written to a file named checkpoint ckpt file.pickle. So I've defined save dump here in line number 4 as ckpt file.pickle. That's quite a name that I came up with. I'm sorry, it's difficult for me to even speak this out or pronounce this nicely. So basically, I defined the name of the file or the dump file at line number 4. And then I use this here in line number 13. So I'm saying in write or dump the state of the code in the file called saved dump, and the saved dump is same as checkpoint file.pickle. So here, if you look now at line number 18 to 22, actually, these lines here. So here we are checking if a file named ckpt file.pickle already exists or not. And if the file exists, that is, a checkpoint was written and the file in which the checkpoint was written is available, then we initialize the value of start to the value written in the file. So there is this variable start here that you see. So if there is no checkpoint file, then start will be set to 0. But if there is a checkpoint file, the value of start is loaded from what is saved in the file. And that's all that is needed to implement this checkpointing and restart feature, in addition to, of course, the other things that the code has, such as here in line number 27, we are giving a prompt to the user, as in press controls, as in if you want to resume, press Y. So I show you how to run this code here on the right side of the slide. We have Python and the name of the Python file. And when I run it, after it has run for a few times, I press Control-C to interrupt it. And as soon as I interrupt, I have the logic written at line number 26 in the code here. So as soon as there is interrupt, there's a prompt given to the user for pressing Y or entering Y if they want to continue. And if they press any other key but Y, the code will exit. And it will save a file, which is the checkpoint file here. So here, after I press Control-C, I see this prompt saying, would you like to continue running the code? Type the letter Y for yes, and I typed Y. And as soon as I typed Y, the code resumed running from where it stopped or from where it was interrupted. So it started from 4. Earlier, before interruption, it was at 3. Now it prints 4, 5, 6, 7, 8, 9, and goes till 13 till I interrupt it again. And if I interrupt and I don't enter Y, the code will exit. Let's look at this second slide related to the same code here. Here I show running the code again. And when I'm running the code again, I actually, I'm trying to show from scratch the whole process. And here I interrupted the code now. After that, I printed 7. And you see here, when I do ls in this directory, there was this file ckpt-file.pickle that got created. And I intentionally removed this file. So when I intentionally remove this file, there is no checkpoint that is saved. Now, when I run this code again, it will start from scratch. So this was just to demonstrate that if the checkpoint file is removed, the code is going to restart from scratch. So you see, when I run that code again, it began computing from 1 and it goes forward. And I keep interrupting and resuming multiple times. Till at a certain point in the end here, I do not press Y, and then I resume the code from the checkpoint. So I have this file, ckpt-file.pickle saved. I do not remove this like before. And when I run this code again, Python ckpt.py, that's how I run the code again. And now this time you see, instead of starting from 1, it's starting from 19. It's starting from 19 because when I interrupted the code, the last value it printed was 18. So it's continuing from where it was interrupted previously. So this is just to demonstrate how you can implement checkpointing and restart mechanism in Python using the pickle package. Now let's look at how would we handle checkpointing and restart in TensorFlow, and also PyTorch. We'll look at that, and also in our code. And here I want to mention that TensorFlow supports 2 types of features, checkpointing and saving. We will cover both of them in a bit. For now, in this slide, let's go over checkpointing and restart offerings from TensorFlow. TensorFlow basically supports checkpointing through a Keras feature, basically indirectly. So here, what you see on the slide, we are using a Keras package, and we are using callbacks here. And here what we are doing is the model checkpoint callback is being used here together with model.fit. So if you're familiar with writing TensorFlow code, then and using Keras, you would know that callbacks are basically nothing but pieces of code that are executed when certain conditions are met. So we are, and they're usually used in certain calls. So here I'm using the callback in model.fit. This checkpointing callback is being used here. I've specified the callback equal to checkpoint callback when I'm running this model. So model.fit has this callback. And what is checkpoint callback? Checkpoint callback is defined using the Keras package, model checkpoint. And here we are basically setting the monitor to val loss. So there you could be monitoring different metrics for your checkpoints, and there are different parameters you could be setting. And basically the required parameter or an absolutely must parameter, which is not provided by default, is the file name that you should give. I think apart from this, majority of the other parameters, there are default settings that could be used if you don't provide those. But this file path is a required thing. And then you can set the frequency of checkpointing. Now in this example, we're setting the frequency for the checkpoint as the epoch, which means save the model after every epoch. And then we are using the monitor. The monitor here determines the model metric, like I said, to be monitored. And we're using the metric val loss. And we're saying that verbosity is 1. It could be 0 or 1. So if it's 0, it means we are running the code in silent mode. If it's 1, then it means we are wanting verbose output. Then we have set the parameter here, save best only to true. Now, if this parameter is set to true, it will save when the model is considered the best according to the monitored metric. So the monitored metric here is val loss. So as per this metric, whenever the best state is achieved, it's going to be written. And the mode we are wanting to do this is in minimization mode, or min. So min is basically used here because we want to minimize the loss. So loss is a metric that you want to minimize. Likewise, if you're using accuracy, you might want to do something else here, right? You want to maximize. So you might want to take a look at your model, see what your metrics are, what you want to monitor, and write your callback accordingly, or your checkpoint callback accordingly. So here, when this would run, it would save the checkpoint state in this file name that we provided in the call. And then this, in this next code snippet you see here, this code snippet will load the model from the saved file so that our model can resume the training from where it stopped previously. So that was about how to do checkpointing in TensorFlow. I should also summarize one more time that there are certain parameters that are in user's control, and we should actually pay attention to our checkpointing frequency. Where are we checkpointing? Is it like at every epoch, or what is our mode for considering the monitor, whether we want to minimize the value or maximize it, etc. I should also mention here something more about Keras. So Keras saves models by inspecting their architectures. This technique saves everything, basically the weight values, model's architecture, the model's training configuration, basically what you pass to the compile method. The optimizer and its state is also saved. And model.save will basically do the job, as in if you're wanting to save the state and not checkpoint. I actually jumped ahead. I should have been talking about the save part on the next slide. Never mind. I'll go to that the next slide soon. And I should also mention here that if you go to this repo here, the complete code for training and checkpointing a TensorFlow model is provided. We're using the sequential model, and the data set that was used is, I think, the MNIST data set in this example. So you can find the complete code with checkpointing available at this link. And I also encourage you to read more about saving and loading with Keras and reading more about checkpointing or model checkpoint. Like I was mentioning, there are differences in saving a state and checkpointing a file on writing checkpoint files, I mean in TensorFlow. TensorFlow provides separate APIs, like I said, for saving and loading the model and checkpointing, while the checkpoints in TensorFlow include the values of the trained parameters used by the models. They do not include any description of the computations that are done with the models. And hence, if the same source code that was used for writing a checkpoint and reading it back is not available, then basically this reading the checkpoint back will not work. So in situations when you only basically need your model weights to be saved, for example, then in such situations, checkpointing is recommended. However, if you want something like a serialized description of the computations that are defined in your model, you want to save those two, then it's better to consider saving the model. And TensorFlow provides APIs for saving the models. If you look at tf.savedModel API and tf.keras.model API, those can be useful for saving the states of the model. Likewise, just to rehash, if you just want to do the checkpointing, take a look at tftrain.checkpointing API in TensorFlow, or the model checkpoint method in Keras, like what we saw in the previous slide. So those are some of the differences between checkpointing and saving the state, and I recommend that you all read more about it at your time at a later occasion. I just wanted to introduce these concepts at this point here. Now let's look at the checkpointing in PyTorch. How do we accomplish that? PyTorch is an open source deep learning framework, and it supports checkpointing by saving and loading dictionaries called state dictionaries. And I would mention that there is a notion of checkpointing and distributed checkpointing, and there's a notion of buffer checkpointing, there's a notion of general checkpointing that PyTorch talks about. and the details of those would be there in the PyTorch documentation. However, I would mention that the distributed checkpoint feature and some of the other types of checkpointing are in the beta phase, the last one I checked. So you wouldn't find, I think, a lot of material online on how to implement those. So you might have to go through the little documentation that PyTorch provides on those topics and evaluate how to use them in your code. However, I would mention that prior to this feature was implemented, life was just fine and normal when we just use the save method available in PyTorch. So I would just do saving and loading basically, and that helped me accomplish the functionality of checkpointing in PyTorch. So saving and loading, and in the documentation of PyTorch, if you see this mechanism of saving and loading state dictionaries and optimizer dictionaries, these would be referred to as general checkpointing. However, the API that you would use is the save and load APIs, or the calls. So here what you see on the screen here is what does the function look like when we are wanting to save the stage. So the data is serialized. When we call torch.save, we can save values or items such as epoch, model state dictionary, optimizer state dictionary, whatever our metric is. Let's say we want to track the loss, we can save that. And the save data, whatever we are saving, it can be reloaded, or you can make the model read these values by using torch.load. And then you can read that into a variable and pass that to load into the state dictionary and the optimizer dictionary. So the complete code for this part as well is in the GitHub repo I pointed to you on the previous slide. And like this tiny URL, if you want to make a note of this. And I would mention here that this PyTorch model that's there in the GitHub repo does the same thing like the TensorFlow model. It is for training a model with checkpointing, and the data set we are using is the MNIST data set again. With that, let's look at how do we do checkpointing in R. So just like we did checkpointing in Python, TensorFlow, and C, we have to identify what is it that we should be saving to a file, and how can we load this data back during the restart phase. It is very simple, as simple as that. In this whole code that you see on the slide, basically we are reading a CSV file in, and in this line where my mouse cursor is right now, or where my mouse is pointing right now, we have read.csv, we have the file named input.csv here, and this file has a matrix inside it. And this data is loaded inside a variable called mat, for matrix, or short for matrix. And this matrix is incremented by 1. When I say mat is equal to mat plus 1, that means all the values in this matrix are going to be incremented by 1. Then I'm printing the matrix. Then I'm saving the matrix in a file called chkpt.rdata. Then I'm calling a sleep function just so that I'm able to observe the code run, and I have enough time to interrupt the code to test the checkpoint and restart functionality. I put in the sleep function here. And then I'm incrementing the value in the matrix again by 1. I'm printing the matrix, and I'm saving the matrix again. So this code is doing very simple operations. And then in the else part, you see I'm checking the length of the arguments passed to the R script for running. And if there is, let's say, a restart flag passed, then basically I read the data from the restart file or the checkpointing file, and I load that value into the matrix. However, if there is no restart file, then the model will load from the input.csv file. Pardon me, I said model, what I meant is the matrix. So here, basically, this is all that the code does. And this code also is there in the GitHub repo. Let me see if I can run this code and actually give you a small demo of how things work. So let me go here. I'm connected to the Stampede 2 system at the Texas Advanced Computing Center, and I'm just getting an interactive access to a compute node now. All right, so let's see. What was my file name here? So let me show you the file that I have here. I hope I have this file here. But it's not available here. So it's not a problem. I can go to my GitHub repo and get this from there. So this is the GitHub repo I was mentioning. And this is all the code samples that we have discussed in the optimizing IO tutorial. And here I should be having a file called ckptrscript.r. Okay. I'm going to copy the contents of this file into a new file. Checkpoint.r. Okay. All right, I have this available here. Now I want to load the R module. Okay, seems like R is not available. Let me try rstat. Module rstate or unknown. So it seems like the packages I would need on Stampede 2 for running this might not be available, but let me do a module spider and double check. There is rstats I could load. Okay. Okay, let me load Intel module first. Now what? Seems like I'm not doing something right, or maybe the module is not set up as expected here. Let me read this again, the message, module spider this. I do have the Intel 18 and the IMPI modules loaded, but interestingly, this package rstats with this version number is not getting loaded. Let me try this again. Notes, it's not available. Sorry. Let me see if anything is there. Nothing. So never mind. So I think this this part is not available here, but as a backup option, I did run this code earlier on a different system, and I should have the output captured here. So if you go to the README file, I in the same GitHub repo, I have added the instruction on how to run the code. So there is rscript testscript.r, and when the code is running normally, there is this is what it would look like. It will print code is running normally, and then when the code is running normally, while it's running, I pressed Control C here, if you notice, and that halted the execution. Once the execution was halted, I reran this code with --args chkpt.r data and entered restart flag and provide the new checkpoint file. So I wanted the old checkpoint file to be separate from the new checkpoint file, and hence I gave a new name for this file. So that's how we would run the checkpoint code in R. So with that, let me make one more attempt just to make sure I'm not doing anything wrong. So module. Load this module. Okay, so the version 3.5.1 that worked here. So now let me go back to this. I'll show you how I'll run this line by line as shown here in the example. Oh no. So you see the model is running, or the code is running normally, and I pressed Control C to halt it. Now once I've halted it, and I want to run this again without passing the restart flag, it will, when I do that, it will really begin from the scratch, as you notice here. So when it began from scratch, it just read 52, 52, and so forth. Now, when I run this with the appropriate arguments for the restart, these are the arguments that I'm going to be copying and pasting here. Oh, my copying and pasting did not work. So let me just type this out in the interest of time. So chkpt dot data, and I'm passing restart new file dot data. You see, when I ran this again, it didn't begin from the scratch. Rather than 52, when we run this, we see our matrix has 53 in it. So this is all I wanted to demonstrate as to how to implement checkpointing and restart in your R code, Python code, when you're working with TensorFlow, Keras in C++ or C. Now, let me actually go back here and let's cover one more important topic, which is connected to checkpointing and restart process. So oftentimes when you are having a long running job, it's not always feasible to be babysitting the job and being on alert, as in, as soon as this previous job ended in which I wrote a checkpoint, then I should be immediately starting a new job using the checkpoint file. So if let's say you are wanting to run a long running job that would take maybe 6 days to run, but the queue or the partition on the system that you're running on only supports running the job for a maximum of 3 days. So like I was mentioning, you can write checkpoint files. However, you can automate this such that after 3 days, when your file has been written, your job can resume for the next 3 days by reading the data that is saved in the checkpoint file. And in order to do this, you need to rely on the Slurm job dependencies, or you need a way to daisy chain the jobs. So what I'm having here on the slide is a basic job. This all I have here is a Slurm job script that has the job name, the output file name, the queue name I want to run this job in, the number of nodes and cores I want to be using, and the time duration for which I want to run this job. And then I load the proper rstats module, and I provide my rscript here, rscript command. Now, when I submit this job, I'll get a job ID generated. Now that I get the job ID generated, I will use that before I submit my next job. So let's say my next job is called my restart job.sh. That depends upon the output created by the job I ran previously. Let's say this job, when I ran test script.r, running this job would produce an output file, let's say, or a checkpoint file. And I want to use this in my second job, which is titled my restart job.sh. And here you would notice that my R script here, this R script command, has all the required arguments for the restarting of the job. So what I do is I just want to make sure that this job doesn't start, my second job, my restart job.sh doesn't start till my previous one has completed, because only once it has generated the checkpoint file, I'll be able to use it in the restart mode in my next job. So what I do is I submit the first job. So when I submit the first job, I get this job ID. And before I submit, when I submit the second job, I add a dependency there. I say spatch dash dash dependency after not okay 1138117 my restart job.sh. It's important to use after not okay here depending upon what you're doing. Like in our case, we are wanting to build checkpointing mechanism. So we are wanting to implement this mechanism, or we are wanting this job to restart only if our previous one was interrupted. And if our previous one was interrupted, its exit would not have been graceful. If we did not have an graceful exit, that's why we are using after not okay. After the previous job, whose ID is 1138117, after it basically ran into interruption or it exited, only then run my restart job. So what you could do is either wait for the job to time out from the queue and then start this, or as your previous job, the one with the ID, let's say 1138117 is running, cancel this job. When you cancel the job, just to test this functionality though, so that way you're creating an interruption, and that in that situation also your job will exit with the not okay status, and that will make your next job to start. So when you do this S cancel, like I've shown here, your next job will start automatically. And this output that you see here was again from the same script that I showed you when I was running the previous code on Stampy 2. All right. Now with that, I would mention that the data transfer related inefficiencies should be addressed at both post-processing, pre-processing, and actually processing stages. So we have covered how to handle the optimization part during the processing of the job, as in what can you do such that your job does optimal IO. However, even before you get your data to the system on which you're running the job, you might want to consider a few things to optimize the pre-processing steps. For example, you might want to consider compressing the data and transferring it from your secondary and tertiary storage media to your primary system on which you're doing the computation. You might want to select an appropriate data transfer protocol like rsync. We covered this topic on day 1 of the tutorial as well. And then during the processing step, like I was mentioning, on day 1 and 2, you might want to consider appropriate options for or APIs for writing your data and reading the data. Make sure that you're not opening and closing small files too frequently in loops and such general strategies that we discussed. I just wanted to mention them on the slide as a reminder. And whatever you would do with the post-processing step, I would say would be similar to your pre-processing step in the sense that now that you have large amounts of data generated through your simulations or job runs, you might want to compress the data and take it to your secondary or tertiary media, and that select the appropriate protocol for the data transfer. With that, I will pause here before we begin with the exercises. And let me actually also go back to the chat window and see if anybody has any questions. Thank you, Diago, for the helpful message. Diago mentioned here that in case anyone is using the Teams web app on Firefox, they would want to use OpenH264 video codec. Thank you for finding that, Diago. It would be helpful for us for our future sessions as well to know.
My pleasure.
Are there any questions, comments, concerns at this point? Let me go back to the Google Doc and see if there was anything mentioned here. Nothing so far. So, all right. So if there are no questions, let's, and if you all are interested, we can do some exercises and activities. Otherwise, we can call it a day as well. It's totally up to you. I'm available right now to do the exercises with you all. So the few exercises I have here are related to Parallel IO that we covered yesterday. I hope that through these exercises, you will get hands-on experience at Parallel IO with MPI, and you would be compiling and executing MPI code, and you would be modifying the MPI code for the exercises to embed the required MPI routines. This message here, or the information here, is on how to connect to the HPC system of your choice and download and compress the GitHub repo. So this link here on the slide, it contains the code samples that would be useful. Yesterday, I shared the Google Drive link also, so that Google Drive also has the same code samples. So you're welcome to get the data directly from GitHub or from Google Drive, or the files directly from those locations, and copy them onto your HPC system of your choice. And then once you have logged in onto the HPC system, copied your data there, you might want to unzip the file titled MPI io.zip and cd into that file. And once you're into that file, basically exercise 0 was about how to get acquainted with the system that you're working on in case you've not run MPI jobs in that system before. If you are already familiar with your system, you don't need to run this exercise 0, but this is mostly to get familiar with how to compile an MPI job, how to submit an SPatch, or how to submit a batch job, how to run the SQ command, etc. So I don't know if anybody is interested in running these exercises, but I can explain all the exercises right now. Then I'll come back and poll and see if anybody wants to do it now or at a later time. So the exercise 0, like I was mentioning, is just to get acquainted with your HPC system and get practice at compiling and running MPI jobs if you have not already previously used the system for running MPI jobs. And then exercise 1 was about modifying a particular API. Let me go back to this exercise here in the GitHub repo, actually. So the exercise 1.c, this is the code that is required for exercise 1.c. So if you would see that here in this code, we are having a call MPI file write at. So this code would not work unless we complete the information here or provide the right arguments here. So here I have put placeholders for file handle, for offset values, and for the data type. And the point of this exercise is that we look up the syntax of MPI file write at, substitute the right values here by looking at the file handle created in the code. For example, if you look at this code here, in one of these lines, I'm not giving the solution right away, but in one of these lines, we create a file handle. So we just need to get that file handle and put that here. One of these lines would have the offset calculated, and then we would want to get the offset, and then we want to provide the right data type. That's all there is to this exercise, and we will compile this code and then run this. So these are what the instructions tell you, the same thing that I just mentioned much more precisely. So it asks you to extend the variable declaration section as instructed. So in the code, there are commands which act as placeholders. For example, here there's a command that says declare an additional file pointer named FHW that will be used for opening a file for writing purposes. We do have a file pointer here, but I guess that's being used for the reading purposes. You're welcome to change how file pointers are used, or but the main goal is how to make this call work, MPI file write at. So you would want to fill in the arguments of this call. And after this line, MPI file read at, there is a comment at line number 28 of the code where you're being prompted to open a file named data file written in MPI mode create and MPI mode write only. So you have to use the write MPI file open call. So line number 25 already shows you what MPI file open call looks like. And here you will open one more file if you need and associate it with the appropriate file name and the appropriate mode in which you want to open the file in. So that's exercise 1. And then of course we will compile the code and run it, and we will run it with 4 MPI processes. And then this is just an instruction on how to view the output of the code. And exercise 2 is about how to use collective IO call. So let me go here to exercise 2. So this is the code that we would need to be modifying for the second exercise. Here we have replaced the MPI file write at function call below with MPI write all. So here, basically, as it says, read the comments in the file for modifying the code, use the MPI file write all function in the specified place in the program. Remember, MPI file write all is the collective version of the write MPI file write and uses the same arguments. So basically, all you need to do is change the name of the function here. All the rest of the arguments can remain the same. So the point of this exercise was to demonstrate how simple it is to go from non-collective mode to collective mode. You just have to change the name of the function or the API in the program to get it to work. And then you will compile the code and run it. And that was all. And just so that you are aware, the solutions to these exercises are also provided in the GitHub repo. So they're here in this directory named solutions. If you're wanting to do this seriously to see how much you are able to do without looking at the solutions, you're very welcome to do so, and you're encouraged to do so actually. And I will pause here. I will stop the recording as well. And if there are any questions, I will take them now. And if you want me to wait while you do the exercise, I will be happy to wait and assist you with the exercises as well.